All right, today I shall talk about the Frobenius reciprocity formula. So let's start with the finite group G, and let H be a subgroup of G. So so we have the map from ZLG to ZLH. The map is simply, we shall take a phi here, a function. So it's a function defined over G. We simply restrict sorry so we simply restrict that function to H. So now, and it's easy to see that if phi is a class function here, then phi restricted to H is also a class function, is a class function on H. As for any H in H, the conjugacy class of this small h in capital H is contained in the conjugacy class of small h in G. And it's also clear that this map is a linear map. So this gives so this is a linear map from the center of LG to center of LH. We shall call this map by race, and in fact from now onwards in our context we will use a different notation for this. So we will, instead of writing the usual set theoretic notation, we will keep writing res of phi, sorry, so we'll rather write res phi on H, or simply when there is no danger of confusion, then we'll simply write res phi. So then we'll simply write res phi. Okay. Sorry, this has become okay. So this is, so we have this map, restriction map, and on the other hand we have another map that we have that we discussed in the last video, that from the center of LH to center of LG. What is that map? We sent any psi to Ind psi. So Ind psi is a Ind psi is a, so in so this Ind psi is a class function on G. So this is a linear map. Let's call this map let's denote this map by Ind from now onwards. So in the last video we proved that this is a linear map. So today what we are going to do is we want to investigate the relation between this res and in, because res is a map from LG to ZLG to ZLH, and here I have a map from here to here. So it's very natural to ask what relation do these two maps have between them. So this is what the content of Frobenius reciprocity formula is. It just says that these two maps are adjoint to each other. Repeat, these two maps are adjoint to each other. So this terminology adjoint has been borrowed from inner product spaces. So in general the scenario is the following, that suppose I have for two inner product spaces V2W, I have a map A and I have a map B. So then we have the notion of adjointness of these two maps. So I have just taken that from here. But as I said, that you don't have to bother about this, what that means in linear algebra. This is just to tell you that the terminology has been taken from some from some more general language. So here what adjointness means is precisely the Frobenius reciprocity formula that I am going to write now. So the formula says suppose we choose suppose that we choose psi from LH, sorry, psi from a class function on H and phi from ZLG, a class function on G. Then what we can do is, so once we restrict this phi on H, so that becomes a class function on H. So therefore, I can consider their inner product. This inner product is occurring in LH. On the other hand, what I can do is I keep phi here and take int phi which belongs to ZLG. Take int psi. Okay. Sorry. Take int psi. So this inner product is happening in LG. So the Frobenius reciprocity formula says these two formulas are equal. So I repeat, these two formulas are equal. Yeah, but since the inner products are happening in different places, different spaces, so we will, so from the context we will understand which inner product. From the context we shall understand that where this inner product is, where the concerned inner product is taking place. But however, if you wish, you can just put some H and G here just to be very sure that no confusion happens. Okay, so this is what the Frobenius reciprocity formula says. So we shall prove that, but before we have to, well, let's see an immediate corollary from that. So suppose that this psi is in particular an irreducible character of H, irreducible character of H, and phi is irreducible character of G. Okay. Well, I think let us also write the representation. Let us also denote the representation corresponding to phi by W, let's say theta, and let this be some u and lambda. Okay. So chi is the theta is the irreducible representation whose character is psi, and lambda be the irreducible representation of G whose character is phi. Now we shall consider let v rho be induced. So let v rho be induced by W theta. Recall that what it means. We can so if this happens, that means that we can regard W as a H invariant subspace of V, H invariant subspace of V, and theta is the restriction. Theta is the sub-representation of rho H, where rho H is just the restriction of rho just on H. So thus rho H is a restriction of the group H on V. So it is customary to denote rho H by simply rho, restriction of rho to H. And again, as I said, that we will simplify it when there is no danger of confusion. So then we can also write this by any of this, and maybe also res V. So it just is, so this one shows that the space is V itself, but the group has been restricted. Okay, so theta is the sub-representation of res V on this W, and this is V becomes V just becomes a direct sum of W sigma, where sigma W sigma is defined as, let's say, rho G W. G is any element in sigma. Okay, so we assume that V rho is induced by W sigma. So that is, so this is what we mean by this. Okay, so we have just recalled what we mean by W theta, what we mean by this, and now from this we shall see the following, that now with this we shall interpret both the sides properly. So if so what happens to this, if psi is the irreducible character of this and phi is the irreducible character of that, then what is this actually? Psi, the inner product of psi and res phi. What is the inner product of psi and res phi? So inner product is happening in H. What is this? Recall that if let's say if uh, chi is the character of if chi is the character of this row, then yeah, if chi is the character, just a minute, maybe I don't need that. Okay, maybe I don't need that. I don't need that, sorry. So what is res phi? So phi is was the character of the representation, right? Phi is the character of the representation of this representation, and then if we restrict this representation, this is the space is U simply. If we restrict this representation, restrict means restriction on H, then what is the character of this restricted representation of representation? It's a representation of H. What is the character of this restricted representation? Simply the restriction of the character of lambda to H. The character of lambda was phi. So basically this is nothing but the character of res U. So thus, in view of that, this just means that this representation, that is theta, this representation, that is theta, and this representation, well, so yeah, so now this is nothing but number of times the representation theta occurs in res phi, that is I should simply write like this, number of times W occurs in res U, right? Because this is an irreducible character, the inner product of irreducible character with another character is just saying that the number of times that irreducible representations occurs in that representation. So this is the left hand side, and what is the right hand side? The right hand side is simply ind psi, inner product phi. So what is ind psi? In the earlier lecture, we have seen that if psi is a character, then ind psi becomes the character of the induced representation of theta, right? The induced representation of theta. So, well, let me just simply set a notation from now on. So if V is induced by, V rho is induced by this, we will write rho as ind GH theta, and again for simplicity we simply write it either int theta. Okay, and again when there is no danger of confusion, we can simply say int W is V. Simply we can say, we will write. So therefore this is, so this actually is nothing but number of times this phi is a irreducible represent, phi is the character of the irreducible representation lambda. So the number of times U occurs in the representation induced by W. Okay. So Frobenius reciprocity shows that number of times W occurs in the restriction of U is same as number of times U occurs in the representation obtained by induction or obtained by induction from W. Okay. Okay. So this is what the corollary is. Now we shall prove this Frobenius reciprocity formula. So recall that irreducible characters form a basis of class functions of any finite group. So therefore, phi is just phi is just the sum of irreducible characters of H, and similar things hold for phi. And now, suppose we prove that this formula holds when psi and phi are irreducible, then from the linearity of the first variable and the conjugate linearity of the second variable, we obtain the formula for any two class functions. I repeat, since any class function is just sum of irreducible characters. Any class function is sum of irreducible characters. So therefore, suppose we establish the equality for phi and psi, irreducible characters of H and G respectively. Then using linearity of the first variable and semi-conjugate linearity of the second variable of inner product, we get this for any class function on H and G respectively. Okay. So thus, in view of that, it's enough to assume that it's enough to show this formula when psi and phi are irreducible characters. Okay. So we will prove the formula. So as I said, that enough to show. So we prove the formula for irreducible psi and chi. Show when psi and chi, psi and phi are irreducible characters. Irreducible characters. Okay. So now for that we need to make a general observation. The observation is very simple. So suppose I have two representations of any group G. Let's say one is on V, and another one is, let's say, on U. All are finite dimensional complex representation. Let this be some lambda. So home, we recall that this home row lambda is so home GVU. So this is nothing but another notation for this. So this stands for set of all G invariant linear maps from V to U. Okay. So it's a vector space. Sometimes so we write it using either of these notations. So yeah. So now we want to see what happens to the so now what we are interested in is the dimension of this. Okay. So assume that chi is the character of rho, and so let's say some so let's say that chi theta, chi lambda are characters of rho and lambda as well. Okay, we just have to see what happens to this. Okay, so we can assume we can immediately get a decomposition. V1, V2, Vk, each Vi is irreducible. Please do not confuse that with the canonical decomposition. Here I am just decomposing that in terms of irreducibles. And similarly, we can decompose U as a direct sum of irreducibles like this. UL. Let I think let chi1 up to chi k are the characters of v1, v2, vk respectively, and similarly here let me rather write theta 1 up to theta l are the irreducible characters of u1 up to ul respectively. Okay, now what we do is, suppose there is a G invariant map from T to from V to U, then what we can do is, so for any I from 1 up to k and L from j from 1 up to L, j from 1 up to L, so what we can do is, first we restrict T on the I on Vi. Let's denote the restriction by Ti. Okay, so thus Ti is a map from Vi to U. Okay, now we project that map on Uj. So and let the projection of Ti on Uj be denoted by Ti denoted by Tij. Okay, so this restriction and then projection, this is not something, this approach, this technique is not anything new to us. We have used that earlier when we were discussing group algebra. So for each I and L, we have a map like this. Okay, so the thing is, so for each T G invariant, we have a collection of TIL where I runs from 1 up to K and J runs from 1 up to L. Okay, so I have a collection from TIL, and each TIL is by definition belongs to home. It's a G invariant, of course it's a G invariant map from Vi to Uj, right? So for corresponding to each T, we get a tuple like this. On the other hand, as soon as I have a collection of maps, a collection of as soon as for each pair I and J, I have a gene, I have one element from here. Then from that I can construct a map from, I can construct a G invariant map from V to U. So what I'm saying is, this establishes a bijection between home set of all G invariant maps from V to U to the direct sum of home Vi Uj. Okay, so I J. Because for any T here, so the map is precisely this. Okay. So given a T, I get a collection of maps like this. And and whenever I have been given a collection like this, from that I can easily reconstruct T, because the reconstruction is very easy. For example, suppose you fix I, then for that I fix I, so Tj is a map from Vi to Uj. So as I said, first fix I. So since from any for fix I for any j I have a map, so from we get a map from Vi to the direct sum of Uj's. Okay, and again for each I I have a map like this. Therefore again from the universal property I get a map from direct sum of Vi to direct sum of Uj's. Okay, so very usual very usual thing that we do with the help of a universal property. So let me just repeat. First I fix any I, then for each j I have a map. So therefore since for that I have a map for a linear map to each uj, so from that we can putting these maps in the tuples, we get a linear map from vi to uj. Well, for your convenience, let me show you the map. So then ti map is nothing but ti1 up to ti l. Since I have maps to each component from so that I can make a map from vi to their sum, and thus we have a map from each I. Then again we use universal property. Okay, so this is a linear map. This is a linear map from here to here. So yeah, so yeah. So now let's come back here. So T goes to this collection, establishes a linear isomorphism between two vector spaces. That the verification of isomorphism, I am leaving that to you. This is quite clear because each T is clear, T is linear, the gene variant, then these are gene variant, and once these are all gene variant, T has to be gene variant, and they are inverse to each other. Linearity is also quite obvious because so all the maps that we start with are linear. So this is an isomorphism. So therefore the dimension of this is nothing but the sum of the dimensions of this. Okay. So the dimension of this is basically, so dimension of this is basically this direct sum I in j. This is quite problematic. Dimension of vi and uj. Okay, sorry. Dimension of home vi uj. Okay. So now let's see what happens to this. So home g vi uj. Remember that both are irreducible. Okay. So if both vi is isomorphic, so is isomorphic with uj as representations, let me say. So therefore, like let me write the work representation. So the representation on vi is isomorphic to the representation on uj. Sorry, not isomorphic to the representation on uj. Then by Schur's lemma, this has to be trivial. So therefore, the dimension will be 0 if they are same. So otherwise, if both vi and w, vi and uj are isomorphic as representation on to some irreducible representation w, then this, in that case, if this is this happens, then this is, so then this is isomorphic to home gene ww, and by Schur's lemma this is nothing but c. Okay, so therefore its dimension has to be 1. So now we see what happens to this fellow. So here each summand has either dimension 0 or dimension 1. So when is the dimension 1? When dimension 1 happens if they are isomorphic as representations. Okay, so now it's easy to see that therefore this is nothing but chi if I just chi I theta j, right? This is what exactly chi, inner product of chi I and theta j is. Because if they are non-isomorphic, then this will be 0. If they are isomorphic, they will be same. So therefore inner product will be 1. So thus what we have is this dimension is actually the dimension of is nothing but chi I theta j. Recall that rho is the chi rho is the sum of chi i's, and chi lambda is the sum of theta j. So therefore from the linearity and conjugate linearity in the first and second variable of inner product respectively, we get this is nothing but chi rho chi lambda. Okay, so thus if in generality what we have seen is, suppose I have two representations, so then the dimension of the space of all G invariant linear maps or homomorphisms from this representation rho to the representation W is nothing but the value of the inner product of their characters. This is a very general observation. Okay, nothing to do with the induced representation, nothing, just a very general observation. So we use this observation here to finish off the proof of Frobenius reciprocity formula. So let's observe so in view of our last observation, what is this thing? This is nothing but the dimension of, so this is nothing but the dimension of, so first the homomorphism. So a homomorphism from psi is a homomorphism from, well, okay, so okay. So let me introduce the write the notation for representation for psi. So assume that sorry, as I said, we shall assume that psi and phi are irreducible representations of H and G respectively. So let's assume that W theta. So W theta is the representation of H for which the character is psi, and U lambda is the representation for which the character is phi. This is a representation of H, this is a representation of G. Okay. So therefore, psi race, this is nothing but, so this is nothing but in view of the general observation that we have made here, so what we get is so this is nothing but dimension of home H invariant maps from W to U, sorry, yeah, H invariant maps from W to U. Okay, this is what we have. Okay, so the gene yeah, and on the other hand, int psi phi is nothing but dimension of G invariant linear maps from well, so here this is just res U, because res U is a representation of H, W is a representation of H, and res U is the representation of H on the same space U. So this is nothing but set of all H invariant maps from W to U, and this is int W U. Okay, we have already discussed in one of the earlier lectures that these two spaces are indeed isomorphic. So indeed isomorphic, so therefore now their dimension has to be same. That's the Frobenius reciprocity formula. And I will just repeat once, and with that I will finish. That this in view of the previous observation, we see that this is nothing but the dimension of the homomorphisms from the dimension of the G invariant maps from, sorry, dimension of the space of all H invariant linear maps from A W to U, and since U is a representation of G actually, so every H invariant linear map extends to a G invariant linear map from induced, the representation induced by W to U, and like every map here admits an extension to a map here, and that, so sending every map to its extension establishes a linear isomorphism between these two linear spaces. That's what we have seen so in one of the earlier videos, we proved that every f here admits an extension. So for us, every year its extension, it admits an extension to here, and then I left it to you as an exercise that that establishes a isomorphism. So assume that exercise, we see that these two spaces are isomorphic, hence their dimension are same. So in particular, these two become same when psi and phi are irreducible characters. And then, as I said, that every class function on H is just every class function on H is the sum of irreducible characters of H, and every class function on G is the sum of the irreducible characters of G, or irreducible characters of G. So from that so in view of that observation, from the semi-linearity of the first component and the semi-conjugate linearity of the second component, we prove this formula for any psi and phi. Again, let me repeat. So how to prove the, how to extend what we have just obtained here, how to extend. So this is when phi and psi are irreducible characters of G and H and G respectively. So from here, how to extend that to any general class function phi and psi? What we do is we break phi and psi in terms as sum of irreducible characters, and then accordingly the whole inner product will be broken into several parts, and on each summand we will appear this kind of, on each summand we will appear an inner product where the things which are appearing are irreducible characters of H and G respectively. So that happens to both the sides. And now corresponding to each, so in that breakup, so each term appearing in that breakup is same as the corresponding term appearing in the breakup of this, because we have proved that for irreducible characters. Now then that shows that entire sum and sum here, so entire sum here is same as the entire sum there. Okay, I hope things are clear. So with that I will stop. So that proves that Frobenius reciprocity formula.